Welcome to this video lecture on the topic general solution of transmission line. So in this diagram, what is the difference between these two circuits? So first one is the electronic circuit and second is the transmission line model. So what is the basic difference? So let's see the answer. The first diagram is given as the lumped network. It consists of all the electronic components in a circuit. So it can be easily determined. So in the case of second diagram, it is a distributed network. So what are the difference between the two? A network which is formed by lumped components like resistors, capacitor and inductors. It is a lumped network. And also distributed network which is formed by using a sections of transmission line. So the parameters can be easily determined because they are fixed at discrete points in the circuit in case of a lumped network, whereas parameters are distributed throughout the length of the transmission line in case of a distributed network. So we can easily recognize the presence of components in ordinary resistor, capacitor and inductors. Example, it is an ordinary electronic circuit. And it is difficult to recognize the presence of components like resistor, capacitor and inductor. The example is the transmission line. So we are going to solve the general solution for the transmission line. So it is used to calculate the voltage and current at a point on the line. So we can take the transmission line which is having the impedance ZL, characteristic impedance Z0 and propagation constant is gamma. So in this diagram, two values V of Z and I of Z. So these are to be calculated. So first of all, we can revise the parameters. In the previous lecture, we have seen the transmission line parameters. So R, L, C and G, where R is the series resistance, L is the series inductance, C is the capacitance between the conductors, G is leakage conductance. And also other parameters are Z, that is series impedance, where it is R plus J omega L, where omega L is the series reactance. And other parameters are Y, that is shunt admittance, where Y equal to G plus J omega C. So omega C is the shunt susceptance. And also in the previous diagram, we have seen the transmission line where S is the distance to the point of observation from the receiving end. And I is current, it is to be calculated, and E voltage between the conductors at any point, and L is the length of the line. So these are the initial parameters to be taken for calculation. So for finding the transmission line solution, a small section of long transmission line is taken. It is shown in the diagram. Then modeled with each small segment with a small series resistance, series inductance, shunt conductance and shunt capacitance. So these are the segments of a transmission line. So for solving the solution, we are taking the series impedance Z into ds and admittance Y into ds, and S is the distance between the receiving end to the measuring point. So this circuit is solved. First of all, voltage drop in the line. So this incremental section of length ds and carries a current I. So in the previous diagram we have seen the T network. So here the series line impedance being Z ohms. So voltage drop D is taken as current into impedance. So I is into ZDS. Okay, this is the voltage drop. So D by ds is taken as I into Z. So like that we calculate the current. So here the admittance is Y into ds. So Di equal to voltage multiplied by Y into ds. So E into Y ds. So Di ds is calculated. Di by ds is equal to E into Y. So next, the previous two equations are differentiated with respect to S, and then d squared E by ds squared equal to Z into Di by ds, and d squared E by ds squared is taken as Z into Ey. So these Previous two equations are differentiated and we get the differential transmission line equation. So these two equations are used to find the voltage and current. And also we are substituting the parameter m for solving the equations. So in this m is calculated as plus or minus square root of zy, and the solution of the equation is given by 9th and 10th equations, that is where a, b, c, d are arbitrary constants of integration. And to calculate the receiving end parameters, it is s is equal to 0 at the receiving end, so I equal to IR and E equal to ER. So we substitute this condition in the previous one, so ER equal to A plus B and IR equal to C plus D. So using this relation, E and I is calculated. So this is one form of general solution where we get the A, B, C, D values to substitute in the arbitrary constant. So these four constant values are to be substituted in the voltage and current equation. So this is the one standard form of general solution. It is in the form of e power values, and another form is the in terms of cos and sin theta. So this is the general solution, another form of general solution where E equal to ER cos h square root of EZY is plus IR into EZ naught sin h square root of EZY s, and also current values. So there are two standard forms of general solution of transmission line. And final solution, it is simplified and useful form of equation for voltage and current are given. The above equations are known as the general solution and equations of voltage and current at any point on the transmission line. So the applications of transmission lines are, they are used to transmit signal, that is electromagnetic waves, from one point to another point, and they are used for impedance matching purpose, and also it is used as stub by properly adjusting their length. Assessment questions. State the difference between lumped and distributed network. We have discussed lumped and distributed elements, example electronic circuits and transmission lines. And what is the need for a transmission line general solution? So it is needed for solving the voltage and current, and some parameters of the line is primary constant and secondary constants, and assumptions at the receiving end are S is equal to 0 and E equal to ER and I equal to IR. The expressions for transmission lines we have derived in this lecture. So thank you for listening this lecture.